Okay. Cool. Okay. Yes. Just say yell. Hello, everyone. How's it going? Anyone do anything interesting this week?
Where is cats?
You want to see cats? I can do that, Wendy.
You're on a mission, I swear.
Cat.
Oh, everyone, if you go back and freeze frame on this recording, you can steal Alad's student ID and therefore his identity. That's how everything works.
Yep, I am uniquely identified by my student ID. This is my dog. He's not a cat. This is a cat. All right.
Are you sure your dog's not a cat? Hot take.
Uh-huh.
Yeah, you're bold by going on just straight up your Google Photos.
I am bold.
This is going to exist into perpetuity, you know.
Yes, my dog wants duck.
And that is forever a part of the first version of this class.
And also your SpaceX stuff.
Oh yeah, Alec worked at SpaceX, everyone.
Oh,
and
that's actually kind of a cool thing. It's not strictly related to this, but it is a fun thing to show pictures of in the 1 minute we have. I worked at SpaceX this summer, and this is part of a Starlink antenna. And as you can see, it's got some cool resonant cavities built into the PCB.
Are you legally allowed to show us this?
I mean, I don't work there. They mailed it to me, so maybe.
That sounds fair game.
Don't tell anyone.
Don't tell anyone, especially not this recording that's going to be up forever for future versions of this class as a model.
I can't tell you what any of these bits do, but they're all really cool. And if you're interested, you should go work for SpaceX.
Okay. Well, only if you're... Oh yeah, it's so easy.
Wow, shilling for SpaceX now, aren't we?
Anyway, we're at 10 minutes past, so real quick, I'll say just a quick reminder that the first homework is due midnight tonight on Gradescope. Some of you already submitted, a few people haven't. We're not going to be super strict with the due dates. It's more just for the sake of we're going to release homework 2 probably tomorrow, and it's in your best interest not to have 2 things like active at once for this class. As a reminder, if you do run over like the allotted time, which should be, I think it'd be 4 hours for this assignment, even though it was a 2-week one. If you do run over that allotted time, you can just leave us a note saying, sorry, this is as far as I got. Here's what I spent a lot of time on. Here's what I spent very little time on, that kind of thing. And then you'll be good to go for credit for this one. So today, Alad's going to be talking us through the basics of computer architecture. Sadly, I can't stick around this time. But I'm sure he'll be keeping an eye on the chat and stuff, and will be available in Discord later. Okay, have fun, everyone.
Yeah, hello, everyone. So today is the computer architecture lecture. I apologize, the homework for this lecture is not out yet. It's going to be delayed by a day or two just because it's a little bit complicated, and we just want to make sure we get everything right. But it will give you, if it's 1 day or 2 days late, we'll give you an extra 1 or 2 days or 3 days just to be sure. Hopefully it won't be too hard. It's just there's a lot of stuff that goes into it that we need to make sure all works. So that, if you do get an error in stuff, you can figure out what's going on. Okay. Does anyone have any questions about logistics or anything before we start? Speak up or say something in the chat. Okay. Today, we are going to be taking a very shallow dive into the topic of computer architecture. And this computer architecture is basically the study of how do you build a processor that you can make on a piece of silicon that is sufficiently simple that you can make on a piece of silicon, but that can perform every operation that you might want to perform in a program and do so relatively quickly. And this is this is a very, very deep subject. It's very cross-disciplinary. There's physics that goes into making fast transistors, deep algorithms research that goes into figuring out how to do things quickly, and it's a very, very broad field, and we're going to be taking a very shallow dive. And although you probably won't ever have to directly write programs to run directly on the CPU in your computer, understanding how it works can teach you a lot about why programs work the way they do, and why some things are faster than others. In the pursuit of this goal, for this homework and for this lecture, I have written a CPU simulator that simulates a very simple processor with instructions that are a lot like the ones that you would find in a real computer. We're going to talk about what all that means in a second. And you'll be writing programs for it in a made-up language that's very, very simple and acts a lot like what you're used to. So what you are hopefully seeing on your screen is a basic schematic of how your average computer is laid out. So we have a central processing unit right here, right? And the central processing unit contains what's called an arithmetic logic unit. So something that can perform computations. So like it can add things, subtract things, multiply things. It contains a register file, and registers are basically like fixed variables. So when a CPU will have, say, 32 fixed variables that it can access and perform operations on, and the ALU can read data from these variables. So these variables might contain, a 1, a 5, a 10, and 100. And the ALU can read the 5, read the 10, add them together, and then write back the result into another register. So it can, that's not addition of 5 and 10. It can write back the result, and you'll get 15, and it'll save that in another register. So you can imagine how you could translate, a simple Python program like, A plus B, so C is equal to A plus B, and then D is equal to C times A, something like that, right, into two equivalent instructions for your processor that, you assign A to the first register, B to the second register, C to the third register, and D to the fourth register. And you just do, you have an instruction that's like add C, A, B, and that will add A and B and store the result in C. And then you have a second instruction that follows that, and that's mult D, so store the result in D, C, A. And this is the basic gist of how every program that runs on your computer eventually runs. You have some very basic instructions. So, multiply, add, divide, subtract. Some things that are kind of like if and else that we'll talk about in a minute. And your program gets translated into those instructions, and it runs on the computer, right? And you use some of these very simple registers here, right? You map variables onto those. So they might be labeled, X0 through X32, right? Or A through G. And you would map variables onto those registers, and you could run your program. And this is really great. You can, run your program, and you've got these 32 registers, and you can run you can do some real computation with only 32 variables. But I mean, of course, there are programs that require more than 32 variables, right? So your normal CPU, you've got your CPU that you put into a socket on your computer, right? Or it's pre-soldered on, and then it connects to some big chips of RAM, right? And if you've ever built a computer, you probably know what RAM is. When we're talking about PCs, they're usually little PCBs that have a bunch of different chips on them. And RAM is basically just like a big list. So it contains, so you can, in memory, you can have data that's like, 1, 2, 10, 15. And if your computer has 100 bytes of RAM, or 100 bytes of RAM, then it can store 100 8-bit values. And most computers these days have numbers that are expressed with exponential notation. So you'll have like, 4 gigabytes of RAM on your computer. And that's a very large number, and I don't remember what power that is, but it's like 10 to the 9 or something ridiculous. And you've got all of this memory to work with, and your computer will have instructions for copying data from memory into the registers, right? So you'll go fetch data from your memory and you'll copy it into a register, and then you perform some operation in the ALU, and then that ALU will write back its result to a register, and then you'll push that data back to memory, right? And this works really well. So if we wanted to, write an example program, we have this little simulator here, and we have we can write our program here, and let's say we want, we can write a little program in our little assembly language, and we can do like add, and then I've called so we can do add, and then we have registers here. They're called like T0 through T1. So T0, and then 1 and 3, and we'll add 1 and 3 and store the result in T0, and then we might add T0 to itself. Right, so this is the little simulator we wrote, and then we would print out that value, right? Oh, let me run this. That's my very long simulator. And I forgot a comma. And so you'll take 1 and 3, add them together, store the result in the register T0, and then you'll add that register to itself. So you have 4, and you add it to 4, and you get 8, and you store that in T0, and you output the result, right? So you can do a lot of operations like this. And this is what most programs are going to end up as. They end up as a sequence of instructions that are stored in memory, right? So you'll have, add, mult, divide, right? And you'll just get all those in memory. So doing a little bit of a deep dive into what registers are. So if you have memory, right, we have basically like essentially infinite storage in memory, right? So why are we operating on these small number of registers, like 32 registers, inside the CPU when we could be operating directly on stuff in memory? And this is a concept that's been played around with a lot, but the answer is basically that your computer might be clocked at 4 gigahertz. And that means that there are 0.2, that means that every clock cycle, if you can perform one operation every clock cycle, that means that you're performing an operation every 0.25 nanoseconds. And if you're performing an operation every 0.25 nanoseconds, that means that if you're accessing some storage, like if you're accessing memory, you need to be able to access memory in 0.25 nanoseconds. Now, it turns out that light in 0.25 nanoseconds, light will travel about 3 inches. And if you've ever opened up your desktop computer, you'll notice that the RAM chips are more than 3 inches away from the processor. I mean, they're even more than 3 inches wide because you have, all this 4 gigabytes of memory. That's a lot. Even on modern processors, 4 gigabytes takes up a lot of physical space. And through copper, the speed of light is often like, a third of what it is in a vacuum. So really, your data, just physically for your processor to operate that fast, needs to be less than an inch away from whatever is performing the operation. And the data needs to go from, whatever storage you're performing the operation from to the thing that performs the operation. The operation needs to happen, and then that data needs to go back to the storage in that amount of time. So that doesn't give you a lot of room. So registers are the way you solve this. You have a small amount of storage that's very close, physically close, and tightly linked to what's performing the operation. And you perform your operations there, and then you read and write from memory. And this is kind of a trend that you'll see, everywhere from the smallest levels of computation to the largest levels. So you have registers that are really close to your processor, right? And after that, you have a cache that kind of sits between. It's like so a cache is a little piece of memory that's directly on the processor, and it might have 4 slots, and it sits between between RAM and the registers, right? And kind of buffers storage between them. And then you have memory, which is even farther away. And then you have your hard drive. Right? And then you have Google's data center. And the time required to access each of these at every level goes up by like an order of magnitude. So this might be 0.25 nanoseconds. This would be about 10 nanoseconds. This is 100 to 1,000 nanoseconds. This can be many thousands of nanoseconds, and then Google's data center is pretty far away. It can be, a couple milliseconds, which doesn't sound like a lot, but if you want to perform operations very quickly, you want it to be close. So registers are basically little pieces of storage on the chip. Each little register is going to have a name. So you might have your argument registers, which store the arguments to a function, right? And they'll be named A0 through A7 on the processor that we made for you, right? And you can store data in them, right? You'll have, on the processor that we gave to you, you'll have what we call saved registers, and we'll get into why we have saved and temporary registers in a minute. And these can also store data. And you'll have temporary registers, and these can also store data, right? So one consequence of this is that if you have one function, right? So that might add 2 things, right? And then you call another function, right? And you set, right? Because these registers are directly attached to the processor, and the processor doesn't really it doesn't have extra sets of registers just to use willy-nilly. When you do this, function A and function B have to share the same set of mapped variables. And how you manage this is you define some convention. So you decide that these registers, the arguments, are where you're going to keep the arguments passed between one function and another. So for example, we called func B with the argument A. So we would store A in here, and then it returns D. So when that function returns, it would keep D in here. And then the saved registers are registers that if func B decides to use one of these saved registers, S1, right? So in an intermediate computation. So if D is doing something, if func B is doing something really complicated, like computing a like, doing a squared plus 3 a to the 5th, plus 7 a to the 9th. It's, like say using a polynomial to compute a Taylor approximation of something, and it decides to use one of these saved registers in that computation. Before it uses that saved register, it has to save the previous value somewhere, usually to main memory. And then before it returns back to func A, it has to, so say it uses S0, right? So in our program here, so func A is using S0 for the variable B. And if func B decides to use it for the value of A squared, right, and it erases B and it replaces that with A squared, before it returns the result to func A, you have to, func B has to get rid of that value of A squared and replace it back with B, and it has to save that somewhere, usually in memory. Temporaries are the opposite. So if func A, say, has B in a temporary, then once it calls func B, it can no longer assume that this temporary T0 still contains B. And you would want to do this, for example, because if func A just returns D, right, it doesn't need B or C anymore after it calls func B. So it can just store B and C in temporaries, and if it func B overwrites them, it doesn't matter. So that's kind of why we have this distinction between saved registers and temporaries. And the reason, and by doing this, we let multiple functions work together. So, if one function calls another, they don't beat each other over the head. And this is an example of an abstraction barrier. It's called a calling convention. And in the homework, there'll be a more lengthy description of what specifically the rules are that functions have to follow to work together for the processor we designed for you. Yeah. So how does a processor actually compute these results? So you'll take one argument from source A, depending on how the instruction is set up. So source A would be, a register. So it could be, T0. You'll take one argument, and then your source B might be T5, right? You'll take another argument down here. And the arithmetic logic unit, which is the thing inside the processor that computes everything, basically, like it computes, it computes additions, multiplications, divisions, everything, will pipe A and B into little boxes, magical boxes that are made out of logic gates and transistors that take A and take B and compute their sum. And it will compute, even if you just do an add, it will compute the addition of A and B. It'll compute the multiplication of A and B. It'll compute, the subtraction of A and B. It'll compute the division of A and B. And based on what the instruction is, it'll select the correct result and push that back into the register file to save that result. And the reason you do this is because you have to make hardware specifically to add, and you have to make hardware specifically to multiply. And it turns out that there's no real advantage to stopping yourself from multiplying when you're also adding. it's easier to just ignore the results you don't need. And this is why you kind of see some idiosyncrasies with how you're used to doing things in Python. Like if you were doing something in Python and you wanted to add two things, you wouldn't also compute the multiplication and the division. And that's because things that you do in programming languages happen sequentially. You move down those lists of instructions. Things that happen in Silicon are inherently parallel. So adding, multiplying, and or dividing two things, or in this case, anding two things, which we'll talk about in a minute, doing that all in parallel doesn't lose you anything, and you actually gain some speed because you don't have to think super hard before you do the operation to figure out which one you want to do. You can just think about which one you're supposed to be doing while you're performing the operation, and then select which one you want at the very end. So something we haven't talked about in this class that almost all processors can do and are kind of important to understand are bitwise operations. So you're of course familiar with addition and multiplication and division, right? Division. One thing that you might not have been exposed to is bitwise operations. And bitwise operations you can think of as basically being the same as the operations that we described for Booleans. So if you have A and B, right, and A and B are both Booleans, and A is true and B is true, then the result is true. Bitwise operations are kind of like that, except because these registers you have, they might, on a 32-bit computer, they'll all contain 32 bits of data. So your numbers are going to be written in binary. So you'll have 0 times 2 to the 0, and then 1 times 2 to the 1, and then 2 times or 0 times 2 to the 2, and 1 times 2 to the 3, right? And your operations are written in binary. So storing only one Boolean in this because a Boolean is just 1 or 0, right? Storing only one Boolean in this 32-bit wide register is kind of a waste. So instead, you have bitwise operations like AND, which AND two registers. So AND A and B would AND A and B, and ABC would AND registers B and C and store the result in A. And what you do is, I'm going to attempt to draw an ampersand. I think that was actually right, which almost never happens. So ANDing these two things, right? You'd compute just the AND of every digit. So 0 and 0 is 0, 1 and 1 is 1, 1 and 0 is 0, and 0 and 1 is 1, right? Now, you have your full set of operations. So you have, OR is often expressed with a double pipe or a single pipe. Or pipe is that key that you never use. That's what you get when you hit shift backslash. And or 0 or 0 is 0, 1 or 1 is 1, 1 or 0 is 1, 0 or 1 is 1. Another very common one that is used a lot is XOR. So, caret is usually how it's written. And XOR is basically if one of the two things is true, but not both of them, then the result is true. Otherwise, it's false. So 0 XOR 0 is 0. 1 XOR 1 is 0. 1 XOR 0 is 1, and 0 XOR 1 is 1. The other type of bitwise operation that is pretty common is a shift. So a shift is usually written with two like less than or greater than symbols, right? So shifting 0, 1, 1, 0 over by 2 would be 0, 0, right? So these are adding on to the side that you're shifting away from. And then you have this 0, this 1, and this 0, right? And then the opposite is, of course, a left shift, which operates exactly how you'd expect. So you fill in zeros on this side, and then you have 0, 1, which are these 2 bits, right? Why is this operation useful? It turns out that this is actually a really fast way of multiplying by a power of 2, right? So if we read off this number, it's 1 times 0 plus, just reading this binary number right here, 1 times 0 plus 1 times 2 plus 1 times 4 plus 8 times 0, which is equal to 6. So this is a 6. And if you shift it left by 1, this will multiply by 2 to the 1. So you'll have 0, 0, 1, 1. And you get 0, 1 times 0 plus 2 times 0 plus 1 times 4 plus 1 times 8. And that's 12. Yeah, that's 12. And of course, 12 is 6 times 2, right? That's handy for multiplying by powers of 2, partially because often multiplication actually takes a little bit longer than all the other operations. Which you kind of makes sense because you want, it's like repeated addition. Multipliers are very big on actual physical silicon. So a lot of times the processor won't even have a multiplication unit. And if you want to multiply by a power of 2, you want to use a shift. And of course, the left shift divides by a power of 2. The final operation that is unlike the others is just not, often expressed with a tilde. Not just inverts everything, right? So those are the bitwise operations. Operations. I just wanted to talk a little bit about it in a slide there. So memory. Going back to memory just for a second. Memory is basically a big list. So your interface to memory is you give it a read address, which is just an index into the list, right? So you have a read address, which could be, one of these things in this column, and it will return whatever was in that cell. So if the read address was 1, then, and this cell had 10 in it, the return would be 10, right? And this is actually because the natural starting point, if you are making numbers, like the natural, like if you are making numbers out of a set of wires, like you have 4 wires, right? The first number is all of these wires are off. So the first number you can express is 0. And if the first number you can express is 0, then that should be your first address. And this is why almost all real programming languages, MATLAB is not a real programming language, just, in case 1D complains. Almost all real programming languages index starting from 0. So they index starting from 0 because that is the first natural address. And if additionally, if you have an array at address 3, right? So an array would take up, the memory address 3, so the array might have 1, 2, 3, 4 in it. The natural way to express this is you have the base address of the array. So the base address of this array is 3. And then you just talk about an offset into this array, right? So you talk about an offset of +1, and that gets you the second element. And this is the second reason why everything starts at 0, because if your offset is 0, that's naturally the first element of your array. If we're indexing at 1, you'd have your base here, and it wouldn't matter what you had here because you'd start at 1 and you'd add your offset and you get here, and you're just wasting this slot. So that's why everything is indexed at 0. And that's the way things really should be. And if you're in a programming language that doesn't do it that way, like Julia, then the programming language is doing it wrong. Aditya is not here, so I can say that. But yeah. Then you have the write interface. So the write interface is basically like setting a list. So you have, memory of 5 is equal to 10, right? And that takes an address 5, and a value 10, and it will go to the 5th element of memory, and it'll set this to a 10. And that's how memory works. Now, I talked about how you use memory to store extra variables, right? Extra variables that don't fit into your registers. But you need an address in memory, right? You need an address 0, for example, to access the 0th element, right? You would need an address, 6 to access this element. So if you need an address, and that address has to be stored in a register, and you're referring to an element, then you're not saving any space because you have a number that you need to access, and you don't have a variable, enough room in the registers for that number, so you're going to put it in memory. But then you need to remember where you put that in your program. And if you're doing that, then you need a register to remember where that is. And this creates an obvious circular problem, right? The way we solve this is, that's not how we solve it. We solve it with a stack. So a stack is a very basic data structure in computer science. It was first mentioned by Turing in like 1945. Well, it wasn't first mentioned, but it was first brought into the zeitgeist by Alan Turing in like 1945. And you can think of it as a stack of plates. So if you go to Crodes, they'll have plates on a spring-loaded little dish rack, right? I actually don't remember if Crodes has one of these, but they do exist. I'm sure you guys have seen them in some cafeteria. And you take a plate off the top, and you got your plate up here, and all the other plates move up. So now there's a new plate on the top, right? And then you put your plate back on this dish because you're a bad person and you don't care if it gets washed. And now all the plates move down, and now your plate's on the top. So this is useful because you can just remember where this stack is. And if that's only one thing to remember, and then you know how to get to all of these things, right? Because if it's the 4th variable in your program, you just gotta, go down 4 elements and access it. If it's the 1st variable in your program, it's on the top, right? And the way we implement this on the computer is in main memory, we have some stack that starts at, say, address 0. And each time we add a variable to it, and Turing called these instructions bury and unbury, but no one in English really uses the word unbury to signify digging something up. So we've decided to call these push and pop. And you'll have a special register in your processor, often called stack pointer, right? And if you push T0, then it will take T0, put it at the bottom of the stack, and then set SP is equal to SP plus 1, right? And then if you push T1, so SP will be here. If you push T1, you'll have T1 in here, and SP will be equal to SP plus, it will be equal to SP plus 1, and your stack pointer will point here. And when you pop something off, so if you do pop A0, that will go to the stack pointer, grab the value that's at the bottom, set A0 equal to what used to be in T0 when you pushed it, and then set SP to SP minus 1, and now your stack pointer points back here. There are whole languages that are entirely stack-based. It turns out that you can, if you have a stack, you can write programs that operate entirely on variables in the stack, and you can always do this. So so for example, if you have an instruction to swap things, that's all you need to implement any program on a stack. Of course, this is like a pain in the ass. So computers don't actually work this way, but it's a neat idea. And for things like a lot of things will be represented with a stack, and then they'll compile to registers. And you might not know what those words mean, but that's okay. Basically, a lot of languages treat themselves internally like a stack machine, and then they use another piece of code that someone else wrote to translate the really slow program on the stack machine to a really fast program on a register machine, a machine that has registers, and then another stack on top of it that's kind of slow. Let's see. I completely did not go with the order that I planned for this lecture. So we're gonna hop over to here. Okay. So just a little aside, I mentioned caches earlier, and you might not know what a cache is, and that's understandable. But like I said, memory is way slower than registers because memory is off the chip usually. It's physically just very far away. The way that we make it seem like memory is a lot faster than it actually is by having small bits of memory directly on the processor. And in that memory, you'll store a data like 5 and a tag. And that tag will be the address in the actual memory that data is located at. So if you have big memory, right, and the tag is 6, then that's 1, 0, 1, 2, 3, 4, 5. That means that there's a 5 here. And because this cache is directly on the CPU, you can access it faster, right? But it's much smaller than main memory, so it might only be able to hold 4 things, right? Yeah, so it might only be able to hold 4 things, right? And if you try to access another thing, it'll clobber whatever you used least frequently out of this cache, and it'll replace it, right? And it lets you make computers that seem a lot faster than they, in theory, look like they should be. And actually, this takes a lot of memory, but a lot of computers actually dedicate a lot of room on themselves to purely just to the cache. So this is an example of the computer that's very similar to the one I'm running on right now. It's an x86 CPU by AMD. Right here are the CPU cores, right? And then each CPU core has a little bit of cache. And when I say a little bit, I mean literally literally larger than the CPU core itself. That's all cache. This is another cache in here. That's another cache. 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 The caches on CPUs are huge because just by increasing the cache size, you can extract a lot of performance for things like matrix operations when you're operating on 1,000 by 1,000 matrices, and the importance of caching is kind of hard to overstate. And most of the optimization that things like NumPy does is writing programs, expressing operations in a way that prevents you from clobbering data out of the cache and trying to keep all of the data that you're currently operating on in the cache. That's where most of the work in operations in optimizing code actually happens. And a lot of that is abstracted away because Intel doesn't like to publish how their caches actually work because that would tell AMD how to make really fast caches and vice versa. So a lot of it's just guesswork. But people have gotten fairly good at that. So the last thing I want to talk about is, we've talked about how you run operations, right? Add, multiply, divide. But like we talked about in the last lecture, if you can just do arithmetic things like adding and subtracting, you're not going to really get anywhere because you need to be able to your computer needs to be able to make decisions. It needs to be say, if X do Y, else do Z. So the way you do those the way we do those on our little CPU and on most CPUs is we have what are called branch instructions. And branch instructions are conceptually pretty simple. So if we have, a stream of, so we have 4 branch instructions: branch equal, branch not equal, branch greater than or equal to, and branch less than. And if we have a stream of instructions, so, add, sub, multiply, right? We might have a branch less than, and then a location. So for example, -2, a relative location, and then 2 things. And if A is less than B, then the branch, instead of executing the instruction that comes next, so like, an add, it'll jump 1 instruction, 2 instructions back and execute this instruction, right? Or you could implement an if-else condition this way by, having a forward branch. So this would implement so if you have a branch and you branch back to this code, you've already gone through this code, so you've got a loop here, and you've made, a loop. So you might multiply 2 numbers and then subtract them, and keep doing this until one of those numbers is less than another number, right? And there'll be an example of this on the homework. Or you can change, branch not equal, branch equal, branch greater than or equal to, et cetera, right? So that's one form of flow control. Instructions usually will execute from top to bottom, but when you hit a branch, they might go back or or jump back or jump forward, right? The other type of flow control is a call. And what a call does is it's basically an unconditional jump. So a call will say, if you have the location of some function, right, f, print high, right? Call f print high will save, and then followed by that, add T0, T0, 1, right? Call will save the address of the following instruction into a special register called RA, often. So RA stands for return address. It'll save the address of this instruction into RA. And then it will do, say if we had, say print is all the way down here, and it just, outputs something. It will jump to here, it'll run out high, and then print will have a return instruction. And what return will do is it will read RA that was set by the call, which points here, and it will change the execution of the program back to here, the next instruction after the call. And this way you can write functions that can be used by used in multiple different other places, right? Because otherwise you'd have to have a jump to a specific place. And then if you had a jump that just jumped right to here, and then you had another call to print high, it would just jump back to here, and you'd have a problem because it's not jumping to the instruction it's supposed to, which is the one, right after the second call. So that's why we have this whole return address thing, right? And basically, the return address, because this call saves the address of this instruction instead, it'll jump back to here when it returns when it's called from here. So that's the last form of flow control. This might have been all very confusing. We only have 3 minutes left. So I want to open this up to any questions you guys have, and please don't be shy. Because I'm basically tossing you into the deep end here, and I feel a little bit bad about that, but I don't want to spend a huge amount of time on this topic because it's not something you're gonna ever interact with directly, but I do want you to get an understanding of how processors work, because it will make a lot of things make a lot of sense. For example, because you store arrays in memory, right? If you're storing arrays and you're storing this array in memory, and the register, you will store the address of that in a register. Points A0 points to up to here, right? That's why things like lists are passed by reference. So if another function changes it, then it will change it in the adder function, because you're changing it in memory, and instead of the processor having a separate copy of it for each function, the processor just, each function has a pointer to the same location in memory. And when your outer function goes to reference the data that your inner function, when your adder function, oh wait, you can't see this, sorry. If you have, the address of this array in A0, then, and you call another function, you pass this array, it refers to the same physical storage in memory. And that's why when you, for example, append something to a list or change a value in a list, and you pass that list to another function, and you pass that list to another function and it changes the list, that change will be reflected in the function that you called the function that changed stuff from, because it refers to the same physical location in memory. And they're both referring to the same thing. Whereas if you had some variable, like, some integer stored in a saved register, so it's equal to 5, right? And you call another function, and it sets s0 equal to s0 plus 5. The rules say that before the function ends, it has to restore s0 to the original value. So that's why things are unchanged. And if you actually use like Python Tutor, for example, you'll notice it creates things called call frames. Like if you were in 61A, what were they called? They were called,
It was like frames.
yeah, they were called environment diagrams. Those environment diagrams actually represent like the physical values in a location on the stack. So the environment diagrams is the stack for a given function, right? And when you call extra functions, the stack just grows down, and then when those functions return, all that stuff gets erased, and you go back to the original stack from the calling function. So like one of the things, like, so for example, if the function needs to use, if the called function needs to use S0, it'll push S0 to the stack.
So I think we're out of time, and I want to make sure I say this before we're officially over.
Yeah.
I think we are officially over, but still. Next week, I just looked at the schedule like yesterday. Next week, Monday is President's Day. So what we're going to do is we're going to switch lecture and office hours. So Wednesday, 7 to 8 is going to be our next lecture. And Monday will be open for office hours, but of course, office hours are mandatory, so you don't have to come to those. And if you really don't want to do anything work related on the holiday, we're happy to set up alternate office hours for next week as well.
Yeah. Oh yeah, sorry, I completely forgot to mention that.
I forgot it too. Don't worry about it.
Yeah. Yeah. If you have more questions about computer architecture, which I hope you do, because if you understood everything I just said, you probably don't necessarily need to be taking this course, although you still should. Please come to my office hours on Wednesday. I think Aditya can probably explain some of this stuff a little bit, but this is a field that I am very familiar with, and I think he's a little bit less familiar with. So if you do have questions about this specifically, please come to my office hours on Wednesday.
Yeah, this is definitely Alan's level of expertise. I'm pretty much learning this with you guys.
Yeah.
And then, of course, we're also going to flip like halfway through the semester when it'll be my area of expertise, and Alan's going to be learning it with you guys.
Yeah. Yeah, so we're over time, so if you need to go, feel free to go. But if you have questions, please ask them. I will be staying around for a couple minutes to answer questions. Does anyone have a question?
Could we stop the recording just in case people have questions? They don't have to be on the record.
Record.